Welcome back to the video series on electrochemistry. We are picking up with galvanic cells. So a galvanic cell is a type of electrochemical cell. And an electrochemical cell is just where you separate the reactants and the products so that they cannot have physical contact. Okay? And you have the electron transfer taking place through an external circuit that connects your separated reactants. So a galvanic cell can also be called a voltaic cell. You'll hear those used interchangeably, but it is a type of electrochemical cell where a spontaneous redox reaction takes place. So when you think of galvanic cells or voltaic cells, think of the word spontaneous. So here is an image of a galvanic cell, and it's pretty important to kind of get an idea of how to sketch this out if you need to. So if you're given a cell notation, you should be able to kind of get this picture in your mind. So you're going to have an anode and a cathode. On the anode side, that's going to be where oxidation occurs, and then the cathode is where reduction occurs. Okay, so in this image, the copper plate is our anode, and then the silver plate is the cathode. Okay, and those are going to be separated into two separate beakers. The anode, the copper plate, will be placed in a copper nitrate solution, and then the silver cathode plate will be placed in a silver nitrate solution. And so you'll have this reaction going between your copper solid and your copper 2 ion. And so since this is where oxidation occurs, you're going to be releasing copper 2 ions into solution. Okay, so you're going to increase that copper 2 ion in solution. And then for the silver, it's the opposite. It's going to be pulling in those silver ions, and those silver ions will be deposited onto that silver cathode. And then in between, you've got what we call a salt bridge. And so the purpose of the salt bridge is to maintain a charge balance in either of those beakers. And so, of course, if you are releasing copper 2 ions into solution, you're going to build up a positive charge. And so the way that you balance that out is having the nitrate ion in the salt bridge that can flow into that beaker. And then same thing with the silver the beaker with the silver cathode, is that you are depositing silver ions on that plate, and so you're removing the positive charge, and so you'll have to replenish that with the sodium ions from that salt bridge. Okay, so the purpose of that salt bridge is just to maintain charge. And then, of course, we're going to have electrons flowing from the anode to the cathode. So we can take that image that we saw and reduce it down to what we call cell notation. And so when we reduce something down to cell notation, just remember that you always start with the anode, and you're going to go from left to right and end with the cathode. Okay, so in that image that we just saw, remember the anode was the copper. And so we're going to start with that copper reaction between copper solid and the copper 2 ion. And you can see the cell notation written in several different ways. So the first notation, you can see that we're including that nitrate ion in solution. But in the second example, we've removed the nitrate and we just focus on the ions that are participating in the redox reaction. So that copper 2 ion. And you do include the phases, and you separate anytime that you have a change of phase, you're going to include a vertical line in between. So you can see that here. And then whenever you are trying to separate your two half cells, you'll represent that with a double vertical line. Okay, so let's practice some of this. We are going to take the cell reaction that we have listed and write a cell schematic. So in order for us to do that, remember that we always start with the anode. right, and end with the cathode. And so in order to do that, we first have to figure out, well, which part of those half reactions is occurring at the anode versus the cathode. And remember that the cathode is where you have reduction, right, and the anode is going to be oxidation. And so if we split this up into our two half reactions, or if we just look at the oxidation number of each, we've got silver and copper, and silver starts out as a positive 1 ion and then ends without a charge, right? So its oxidation state is 0. And then copper is the opposite. It starts out with an oxidation state of 0 and ends with a positive 2 oxidation state. And so which one is being oxidized, which one is being reduced? You can see that the oxidation number is decreasing for that silver, and so that's the one that's reduced. And copper then must be oxidized as it's increasing in charge. So reduction would be the cathode. Okay, and that must mean that copper represents your anode. Okay, so knowing all this, once you figure out what part is your cathode, what part is your anode, then we can start with that anode first. And remember, we want to start with the solid piece of it. So we're going to start with that copper solid on the reactant side. Draw that vertical line to separate copper from its product, which is the copper 2+ ion. And include those phases. Oops. And then have a double vertical line to separate one half reaction from the other. And then you can begin with the solution that the cathode is placed in. And so that is your silver ion. Followed by your solid silver plate. And notice how in all of these reactions, right, we're ignoring the coefficients. And that's because when we're looking at cell potentials, that those are intrinsic properties, and so we tend to ignore any of the coefficients in those equations. Okay, let's try one more practice. This time we're given the cell notation and we are asked to write out the balanced chemical equation. Okay, so again, we're going to split up those two half reactions. We can write out the first one where we've got nickel as a solid going to nickel 2+. Okay, and then below that, happening at our cathode, we've got the silver ion forming your solid silver. And we go back to those balancing half reaction steps. Remember, the first step is to make sure that all elements other than oxygen and hydrogen are balanced, which they are. Then we would add the water molecules or the hydrogen ions if we had any hydrogen or oxygen, which we don't. And so the next step is to balance those charges using electrons. And so, of course, the ion side is going to have a larger charge. And so we add 2 electrons to the side for nickel and 1 electron to the reactant side for silver. And then we have to get those electron numbers to be the same on both sides. And so, of course, we're going to have to multiply that second reaction by 2. And so basically that just makes everything a 2 in front. Okay, and then the electrons can cancel out on both sides as long as they match. And then we add those reactions together. And so we get that nickel solid reacting with 2 silver ions. And that will give us the nickel 2 ion plus 2 solid silver. Okay, so again, using those skills from balancing half reactions and using that half reaction method. So the next topic we're going to look at are electrodes and cell potentials. So a potential reflects the driving force for a transfer of electrons between redox reactants. And we measure this potential in units of volts, keeping in mind that the definition of a volt is 1 joule of energy per 1 coulomb of charge. So a volt is equal to J over capital C. A half cell potential can only be assessed if you have another half cell to compare it to, right? It's a driving force, it's a transfer of electrons, and so you have to have both half cells present. And so a cell potential is going to be the difference in potential between the two half cells. And what's important here is that you always take the potential of the cathode minus the potential of the anode. Okay, and this is opposite of that cell notation, right? So cell notation always had the anode written first, cathode written second, or at the end. And so with a cell potential calculation, it's going to be opposite, right? Cathode minus the anode. Now we can have standard cell potentials. Remember that if you have a standard of anything, it's denoted by that degree symbol. And standard state conditions for a cell potential are going to be 1 molar concentration, 1 bar pressure, and 298 Kelvin. So if we have to have both half cells present in order to measure a cell potential, and we want to calculate, if we want to have a table that lists all of the cell potentials for our different half cells, then we need a reference. And so the reference that we use is the standard hydrogen electrode, the SHE. Okay, it's just the half cell that has been decided upon, where we give that a cell potential of exactly 0 volts. And if we do that, then we can compare everything else to it. Okay, so this SHE, it contains an inert platinum electrode, and it's immersed in 1 molar aqueous of your hydrogen ion and a stream of hydrogen gas at 1 bar pressure, and all of this maintained at 298 Kelvin. So keeping all of those standard conditions, right? And so we can use that as one of the beakers and then compare it to any of the other half cells that we want to. And so when we measure the electrode potential, remember that that SHE will always be acting as the anode, and then whatever your reaction of interest is, that's going to be the cathode. So in this picture here, you can see that you've got your SHE on the left-hand side, and then the reaction of interest, right? We've got that copper and that copper and copper 2 ion half reaction happening on the right-hand side. And so just keep in mind that if you were to ever use a voltmeter, the SHE, the anode, is going to be your black, your negative end, and the reaction of interest, that's going to be the positive end, or the red side of your voltmeter. So with that SHE, we can calculate a whole list of standard electrode potentials, and you can find that in your textbook or online. But what's important is that when you're looking at this table, okay, a spontaneous process is going to be described by a positive cell potential. A non-spontaneous process is when E cell, or your cell potential, is negative. And so how do we figure this out? Well, when we look at that list of reactions, right, your oxidizing agent, your stronger oxidizing agent, will be at the top, will have the greater standard electrode potential. And so let's see what this looks like in a table real quick. Right, when we look at a table of standard reduction potentials, notice how they are decreasing as we go down the table. So your oxidizing agent, your oxidant, is going to have the greater electrode potential, and so it's going to be found at the top of that table. And as long as E cell is positive, as long as our cell potential is positive, which means that our cathode is going to be greater, the cell potential of the cathode is greater than that of the anode, then we're going to have a spontaneous process. So basically, if your oxidant entry is above that of your reductant entry, you'll have a spontaneous process. And so what that means is that, if we had, say, F2 reacting with, or let's take it down a little bit farther so we can see the positive and negative charges. If we had, say, gold reacting with a chloride ion, the gold would act as the oxidizing agent, and the chloride ion would act as the reducing agent. Okay, and so in that case, you would have a spontaneous process because the oxidizing agent is higher up on that table than the reducing agent. And also keep in mind, I've said this before, standard electrode potentials are intensive properties, and so we don't care about the stoichiometric coefficients when we're calculating the cell potentials. So let's look at some examples. Which of the following species is the best oxidizing agent and which is the best reducing agent? And we're looking at this list here underneath. Okay, so keep in mind that when you are looking at a table that these are all reduction reactions. Again, because we assumed that the SHE was the anode, right? And the oxidation reactions occur at the anode. And so all of the standard cell potentials that we get are reduction reactions. And so in that case, that means that all of your reactants over here, these are your oxidizing agents. Right, so that's happening on the reactant side. On the product side, those are going to be your reducing agents. Okay, so when they're asking what is the best oxidizing agent, it has to be something on the reactant side. And so the only options that you have are that silver plus ion, which we see on the reactant side here, and you've got your copper 2 plus ion, also on the reactant side here. And that may be it. I think everything else is on the product side. So of those two, your oxidizing agent is going to be the one that is highest up. Remember that your strongest oxidant is going to have the highest cell potential, and so, or the highest standard potential, and so that's going to be your silver ion. So that is your best oxidizing agent. Now, when we're looking at reducing agents, now we're looking at the product side. And so that means everything else could be your reducing agent. And we want the one that is the worst oxidizing agent, right? The weakest oxidizing agent will produce the best reducing agent. And so if your oxidizing agent is in the top left-hand corner of the table, your reducing agent is going to be in the bottom left-hand side of the table. So bottom product side will be your best reducing agent. And that would be your solid copper here. So copper is the best reducing agent. And then at the top reactant side, will be your best oxidizing agent. Okay, now let's calculate the standard cell potential for a reaction. Now, in order to do this, again, we have got to decide what is your cathode and what is your anode, because the equation for your standard cell potential, remember that is the potential of your cathode minus the potential of your anode. Okay, and cathode is where your reduction happens. Right, so we're looking for what is reduced, and then minus the anode, that's where oxidation happens, so we're looking at what is oxidized. And so let's again look at those oxidation numbers on the reactant side and the product side. We've got copper and silver. So copper is starting out as an ion with a +2 charge and going to copper as a solid with an oxidation number of 0, and silver is doing the opposite. It's starting out with an oxidation number of 0, becoming an ion on the product side with a +1 charge. And so the one that's being reduced in oxidation number, that is your copper. Right, so that's reduction, which must be your cathode. And your silver, therefore, is oxidized, and that's your anode. Okay, so then we just look at the table that we're given, or you can look a table up online if you need to for your homework, and find the copper 2+ ion here. Okay, and that is your cathode, so E cell will be equal to 0.34. And remember, all of these are in volts. So if you look back at one of the other examples, top of the table, all of those are going to be in volts. And then minus the anode, which so you're looking for silver, and that's here at the top. So that's minus 0.7996 volts. And if we are using significant figures, it looks like based on that table, the copper ion only goes out 2 significant figures, so our final answer has to go out 2 decimal places as well. And so we get negative 0.4596, and so that will, of course, round up to negative 0.46 volts for our final answer. And then they ask, is it spontaneous or not? So remember, spontaneous reactions have to give you a positive E cell value. And this is negative, and so we're going to say that this is non-spontaneous. Okay, let's try one more. Calculate the standard cell potential. This time we're giving cell notation. And so you've got to remember with cell notation, the first thing written, you always start with your anode and end with your cathode. Okay, so E cell is going to be cathode minus the anode. So just remember that it is opposite. Okay, so we're looking for that silver ion first for your cathode. And that's the 0.7996 volts minus the cell potential for your anode, that's your nickel. So minus a negative 0.257. Again, that goes out 3 decimal places, and so our answer also needs to go out only 3 decimal places, and that should give us 1.057 volts for our final answer. And asking whether it's spontaneous or not, this is a positive right? Positive 1.057 volts, and so that is a spontaneous reaction. Remember, we're just looking at the sign. Positive is spontaneous, negative will be non-spontaneous. Okay, that is it for this section. In the next section, we'll talk about how these cell potentials relate to Gibbs free energy.